In this video, we discuss how vectors can be partitioned into subvectors. We show that the inner product, also called the dot product, of two vectors can alternatively be computed as the sum of the dot products of subvectors. We then show how this leads to a notation that tracks regions of the vector so that algorithms naturally capture how we explain them at a higher level of abstraction. Let's start with a concrete example. We will compute the dot product of two vectors of length 5. Now, computing the dot product of two vectors is the same as multiplying a row vector, that is the transposed first vector, times the second vector. We multiply the first pair of components together, then add the product of the second two components, and so forth. We can generalize and discuss how to compute the dot product of two arbitrary vectors, x and y, of length n. The individual components are now denoted with the Greek letters chi and psi. The dot product is the sum of the products of the corresponding components. We can express this as an enumeration, or with the summation symbol, sigma. Going back to the concrete example, let us think of the vectors as consisting of their first elements and the rest of the vectors. We denote this partitioning with a line. We now notice that the dot product of the vectors is the product of the first two elements added to the dot product of the rest of the vectors. We can do the same thing with arbitrary vectors x and y. Again, the dot product of the vectors is the product of the first two elements added to the dot products of the rest of the vectors. Next, we partition the vectors into the first two components and then the rest of the vectors. Think of this as a top subvector and a bottom subvector. Now the dot product is equal to the dot product of the top subvectors added to the dot product of the bottom subvectors. Again, we can do the same thing with arbitrary vectors x and y. We now see that partitioning the vectors and then taking the dot product is the same as splitting the summation over two ranges. Finally, we partition the vectors into three parts, where the middle part is just a scalar. The dot product of the vector is now equal to the dot product of the top subvectors added to the product of the middle scalars added to the dot product of the bottom subvectors. We can generalize this for arbitrary vectors x and y as well. In the first example, we take the middle part to be scalars, while in the second example the middle part is also a vector. It is now easy to see that if one partitions the two vectors into N subvectors, such that corresponding subvectors have the same length, then the dot product of the two vectors is simply the sum of the dot products of corresponding subvectors.